Hi, I'm Ganning, and I'm going to introduce our work, SemST, Semantically Consistent Multi-Scale Image Translation with Structure and Texture Alignment. So I'm going to introduce these four parts. First, to begin with, I'm going to introduce the background. Image-to-image translation is actually a domain mapper, and the objective is to transform images of the source style to those of the target style with content consistency. For example, we have the input images from the source domain and output images actually from the translated domain. And we also have the target images in the target domain. So what we are trying to do is to translate the images from source domain to translated domain. And the source domain and translated domain have the same content, while the translated domain and target domain have the same content. And it is very important and has many applications with respect to image manipulations, and it can also be used to improve the performance of downstream tasks. For example, the unsupervised domain adaptive semantic segmentation, UDA. And our motivation is that there are many limitations of prior works. For example, the distortion exists by the bidirectional structure, which is the currently most popular strategy. And also currently image-to-image translation methods are only applied on low-resolution images and cannot be applied on high-resolution images. And it also has a semantic distortion, which means the difference between the input and output with respect to their semantic meanings. And also there exists the negative positive coupling effect, NPC effect, in contrastive learning-based method, which will cause the gradient vanishing. And to solve this problem, we propose the contrastive learning-based method, and it is one-sided structure, so we can reduce the distortion caused by the bidirectional structure. And to make the method applicable on higher resolution images, we propose the multi-scale mechanism. And to reduce the semantic distortion, we have a structure and textual alignment strategy. And to reduce the negative positive coupling effect, we use the hard negative mining. And then I'm going to introduce our proposed method. So this is a method overview. So we have two branches. One is the global context learning branch to predict the global predictions. And also we have the local detail learning to predict the local detail crops. And then we fuse the local and global predictions together to get the final output. And we also have a discriminator to learn the features from target domain. And then I'm going to introduce the novelty. First, we propose the multi-scale framework for higher resolution images. As we said, we can predict the detail and context props respectively on the global context learning and local detail learning branch. And to fuse the local and global predictions better, we also have a scale attention head, which is used to learn the features in different scale, and the output of this feature attention head is the scale map. And the scale map will tell us the attention to local details or global context. Then we have the final output prediction, which is used by the local global predictions and the scale maps. Secondly, we reduce the semantic distortion by introducing the TS loss. And the objective is to align the texture and structure representations between input and output to reduce the semantic distortion. So this figure shows the features in different layers in the shared embedded space, and the red bounding boxes represent the receptive field. And we can see that from shallow to deeper layer, the receptive fields go from smaller to larger. And the features also represent from texture to structure information. And we propose a method to align the representations by maximizing the mutual information between the input and output in their shared embedding space. and we use the relative squared loss neutral information. So this is our loss function, TS loss. Third novelty is that we reduce the NPC effect. As we said, NPC effect is caused by negative and positive coupling effect. For example, if the negative samples is too easy, then it is less informative and will cause the gradient vanishing in training. So we propose our HDCE loss to solve that problems. And the objective is to utilize more informative negative samples. So for example, the main idea is to reweight the negative samples based on semantic correlation. For example, we have many blue negatives and the purple query, and we compute the correlation between each negative and query as a new weight to each negative. Then we in the loss function, we reweighting the negatives based on their correlation to the query sample. And we also combine the loss function with the decoupled contrastive entropy loss to further reduce the NPC effect. So our full objective will be that first we use the TS loss in the shared embedding space to reduce the semantic distortion, and we also use the HDCE loss to reduce the NPC effect. And finally, we also apply the Ganning loss to learn the attributes from real from target images. So this is our full loss function. And then I'm going to introduce the experimental results. So first, we apply our method on different image-to-image translation tasks, include GTA5 to cityscape translation, cityscape parsing to image, and photo to map translation. So with respect to the first two datasets, we can see that our method is state-of-the-art. And although for the last dataset, our performance is not the best, but it performed the best in the contrastive learning-based method because photo to map is a paired image-to-image translation, which gives some merits to bidirectional image translation. And then I also show some qualitative visual comparison of our method and other methods. So on this GTA5 to cityscapes dataset, we can see that as shown in the red bounding boxes, there are many artifacts and semantic distortions in other methods, but our method reduces the semantic distortion and has less artifacts, has the best visual performance. And on the parsing to image dataset, we can see that similarly, we have less artifacts. And we also show results on summer to winter translation and horse to zebra translation. And we can see that we have superior or comparable authentic color representation and fewer artifacts. Then I also show that our method can also be applied to enhance the downstream semantic segmentation UDA task, because in UDA they are trying to train images from the source domain and apply the semantic network on target domain. So what we did is to incorporate our translated images in the training of UDA so that we can reduce the domain gap in image level. And from the experimental results, we can see that for both GTA5 to cityscapes or Cynthia to cityscapes datasets, after incorporate our method, we can improve the mean IOU. And qualitatively, we can see that after incorporating our method, we have more accurate label predictions and refined borders. Then I will show the evaluation study, and we can observe the contribution of each component to the final performance improvement. After deleting either part of our method, we can see the performance degradation quantitatively. And qualitatively, we can see that Without multi-scale mechanism, we have inaccurate predictions and the results look blurry. And if we delete the HDC loss and TS loss, we can see more artifacts and semantic distortion. And if we increase the weight of the TS loss, we can see that we have less artifacts and less semantic distortion, which also prove the efficacy of TS loss. Finally, I'm going to conclude my talk with the contributions of our work. So we proposed a novel image-to-image translation method that reduces semantic distortion and NPC effect. Our method is also applicable to higher resolution images, and it has the state-of-the-art performance, and it can also be beneficial to downstream tasks like UDA. So that's the end of my presentation, and thanks for your listening.